So using complex variables, evaluate the real integral, this problem here. So the first thing is to convert the integral into the variable z. So solution. So let z be e raised to I theta, and then cosine of z is given by 1/2 into z plus 1/z, and the theta, by definition, you'll get the z over iz. So we use these values to rewrite this integral in terms of the variable z. So this implies integral from 0 to 2 pi of sine squared theta over 5 minus 4 cos theta, the same as, so this is the theta, I have integral 0 to 2 pi of 1 minus cos 2 theta divided by 5 minus 4 cos theta, the theta. Please note that sine squared theta is what gives 1 minus cos 2 theta over 2. So that's why we have cos 2 theta and we have factored out the half. So next step, we'll write this one as, so let this one be the integral. Let's call this integral I. So then we say I, real part of the integral 1/2, 0 to 2 pi of, I can rewrite this one now, because remember, if the angle is 2 theta, then as a complex number will be cos of 2 theta plus I sine of 2 theta. So 1 minus cosine of 2 theta minus I sine 2 theta over 5 minus 4 cos theta, the theta. So this one is a general one, but we are interested in only finding the real part. And remember, the reason why this is minus is because this is the point I'm fixing the value cos 2 theta plus I sine 2 theta. So because they are bracket, then when I have multiplied by negative sign, then negative sign on this term, negative sign on this term. So this is a general one, but now we want to fish out the real integral from this general complex integral. So this would be the same as real part of 1/2 integral from 0 to 2 pi. And then you can write the numerator as 1 minus. So this in exponential form is e raised power 2I theta, then divided by 5 minus 4 cosine of theta, the theta. Then, since z is given by e raised power theta I, then it implies z squared is what gives e raised power 2I theta. So therefore, I is the same as the real part of a half integral now along C. Now I want to now transform everything in terms of Z. So it will be 1 minus Z squared, 5 minus 4. But where there's cos theta, we have said the answer is the same as Z plus 1 over z, and then the theta is the same as dz over I z. And you specify that C is a unit circle with center z equals to 0. So this means that I is the real part of the integral I have along C. Now let's simplify these parts. So we have 1 minus z squared. You see, I have this I can factor it out, so I put here I. Z I multiply by every term here, so I'll have 5z minus 4 times z is z squared, minus plus is minus, z times z is 1. So that's what we have. Oh, there's a 4 here. So this 4 by this. So this term of 4 here. But you see, then there's a 2. Because remember, cosine of z from what you have defined here is a half. So you need to factor that half outside. So there's a 4 over 2 here. So then this is over 2, this also over 2. And then we have dz. So I is a real part of 1 over 2I integral along C, and then 1 minus z squared, so 5z minus 2z squared minus 2 dz. So which we can write as 1 over 2I integral along C of z squared minus 1 over now 2z squared minus 5z plus 2 dz. Remember what we are doing here, we are factoring negative on the numerator, so we have negative 1 into z squared minus 1, and then factor out negative, so we'll have 2z squared minus 5z plus 2. So this negative and negative cancels out, so that's why we have this solution. So remember, this is the real part of this integral. So I is the real part of this integral. So let's call this portion, let's call it I1. So I1 is given by integral along C, z squared minus 1 over z 2z squared. Now this is 2. Now this is 5. Okay, 5. Minus 5 z, and then plus 2 dz. So here the function f of z is z squared minus 1 divided by 2z squared minus 5z plus 2. Poles are the solutions of this denominator equated to 0. So here, let's say product is 4, sum minus 5. Are there numbers? And minus 4 and minus 1 work? Yes, they should. So 2z squared minus z minus 4z plus 2 equals to 0. Pair this, so we'll have z into 2z minus 1 minus 2 into 2z minus 1 equals to 0, which implies z minus 2, 2z minus 1 equals to 0. And this means z equals to 2 and z equals to a half are the poles of f of z. Now, once you get the poles, you identify those ones which are within the unit circle. Those which are outside the unit circle, then they are excluded from the computation. So of these two poles, only z equals to a half lies within the unit circle. So let's calculate the residue for this pole. So residue at z equals to a half will be limit as z approaches a half of z minus a half times the function f of z. So remember, this is our function f of z. So z squared minus 1. So this will give us limit z approaches a half z minus 1 over 2. So f of z is z squared minus 1 divided by z minus 2 2z minus 1. And this will be limit as z approaches 1 over 2, z minus 1 over 2, z squared minus 1. So here I factor out 2, so I say 2, z minus 2. Then I'll have to write z minus a half. So this expression and this one are the same. By doing so, this factor and this factor cancels out. And so I'll have limit z approaches a half z squared minus 1 over 2 into z minus 2. So now direct substitution should work. So this will be a half squared minus 1, 2 into a half minus 2. Half squared is 1 over 4. 1 over 4 minus 1 is 3 minus 3 over 4. So minus 3 over 4 over a half minus 2 times 2 is minus 3. So minus 3 over 4 divide minus 3 is 1 over 4. So this gives us 1 over 4. Now by residue theorem, I1 is 2 pi I times sum of residues in C, so which is the same as 2 pi I times 1 over 4, because that would, in C we had only one pole which was within the circle C. So this will give us pi I over 2. So remember why I1 is this part, so which is giving us pi I over 2. So which means then the correct value will be 1 over 2I. So therefore I is 1 over 2I times the value in I1, which is 1 over 2I times pi I over 2. Now this should be pi over 4, because this I and I cancels out. So this is the solution to that problem. Thank you.